Welcome to this section on further mechanics and thermal physics. In this topic, we will explore motion in more detail, including circular motion, simple harmonic motion, and gravitational fields. We will also look at how particles behave in gases and how energy transfers through thermal systems. Specification overview and key themes: circular motion and centripetal acceleration, angular speed, radians, and centripetal force, simple harmonic motion, conditions and definition, graphs and energy changes in simple harmonic motion, oscillating systems, mass, spring and pendulum, force vibrations, resonance, and damping. In further mechanics, students study circular motion, simple harmonic motion, SHM, oscillating systems, and resonance. These ideas are central to understanding real-world systems such as satellites in orbit, suspension systems in vehicles, musical instruments, and seismic vibrations. A key emphasis is placed on linking mathematical relationships to physical behavior, for example through the interpretation of displacement time, velocity time, and acceleration time graphs. Thermal physics complements this by focusing on internal energy, thermal energy transfer, ideal gases, and the molecular kinetic theory model. Circular motion occurs when an object moves at constant speed along a circular path. Although the speed remains constant, the velocity is continually changing because its direction changes, meaning the object is accelerating. This acceleration is always directed towards the center of the circle and is known as centripetal acceleration. The magnitude of centripetal acceleration is given by equals v squared r, where v is the linear speed and r is the radius of the circular path. This can also be expressed as a equals squared r, where omega is the angular speed. Angular displacement is measured in radians, where 1 radian is defined as the angle subtended at the center of a circle by an arc equal in length to the radius. Angular speed omega is the rate of change of angular displacement and is given by omega equals v r equals 2f, where f is the frequency of rotation. Using radians simplifies many equations in mechanics because it leads to more natural mathematical relationships. The centripetal force required to maintain circular motion is given by F equals mv squared r, or equivalently F equals m squared r. Simple harmonic motion, SHM, is a specific type of oscillatory motion defined by a precise mathematical condition. The acceleration of the object is directly proportional to its displacement from a fixed equilibrium position and is always directed towards that position. This is expressed by the defining equation equals squared x, where x is the displacement, omega is the angular frequency, and the negative sign indicates that the acceleration is a restoring acceleration. SHM is an idealized model but provides an excellent approximation for many real systems, including mass spring systems and simple pendulums at small angles. In SHM, the motion is periodic, meaning it repeats itself at regular intervals, and key quantities such as displacement, velocity, and acceleration vary continuously with time. Graphical representations are central to understanding simple harmonic motion. In SHM, displacement, velocity, and acceleration all vary sinusoidally with time, but they are out of phase with each other. The displacement time graph is typically a cosine or sine wave, while the velocity time graph is shifted by a quarter of a cycle, and the acceleration time graph is in antiphase with the displacement. The maximum speed occurs at the equilibrium position and is given by v_max equals a, where a is the amplitude. The maximum acceleration occurs at the extreme positions and is a_max equals squared a. Energy changes in SHM provide another powerful way of analyzing oscillations. The total mechanical energy of an undamped SHM system is constant and is shared between kinetic energy and potential energy. For a mass spring system, the time period of oscillation is given by T equals 2 pi square root m e k, where m is the mass and k is the spring constant. This equation shows that the period depends on the mass and the stiffness of the spring but is independent of amplitude, provided the spring obeys Hooke's law. For a simple pendulum undergoing small angle oscillations, the period is given by T equals 2 pi square root Lg, where L is the length of the pendulum and G is the gravitational field strength. The small angle approximation is essential here, as it ensures the restoring force is proportional to displacement. Force vibrations occur when an oscillating system is driven by an external periodic force. The behavior of such systems is strongly influenced by resonance, which occurs when the driving frequency matches the natural frequency of the system. At resonance, energy transfer to the system is maximized, leading to large oscillation amplitudes. Damping refers to the loss of energy from an oscillating system, often due to friction or air resistance. Increased damping reduces the amplitude of oscillations and broadens the resonance curve, making the resonant frequency less sharply defined. internal energy and thermal energy transfer, specific heat capacity and latent heat, ideal gases and the ideal gas equation, molecular kinetic theory of gases, required practicals, exam technique, and summary. Thermal physics focuses on internal energy and how it changes as energy is transferred to or from a system. Internal energy is defined as the total random kinetic energy of the particles and the potential energy associated with the forces between them. Changes in internal energy can occur through heating or through work done on or by the system. The first law of thermodynamics summarizes this relationship as U equals cube W, where U is the change in internal energy, Q is the energy transferred by heating, and W is the work done by the system. Specific heat capacity and latent heat quantify how much energy is required to change the temperature or state of a substance. The specific heat capacity C is defined by the equation E equals mc, where m is the mass and is the change in temperature. This equation applies when there is no change of state. Latent heat, on the other hand, refers to the energy required to change the state of a substance at constant temperature and is given by E equals ml, where L is the specific latent heat. The ideal gas model provides a simplified description of gas behavior that is accurate under many conditions. According to this model, gas molecules are treated as point particles with negligible volume, no intermolecular forces, and perfectly elastic collisions. The macroscopic behavior of an ideal gas is described by the ideal gas equation PV equals nRT, where P is pressure, V is volume, N is the amount of substance in moles, R is the molar gas constant, and T is absolute temperature in Kelvin. This equation combines Boyle's law, Charles' law, and the pressure law into a single relationship. The molecular kinetic theory model explains gas pressure and temperature in terms of the microscopic motion of molecules. Pressure arises from the transfer of momentum when gas molecules collide with the walls of a container. The kinetic theory equation PV equals 1/3 nmc squared links macroscopic quantities to microscopic properties, where n is the number of molecules, m is the mass of one molecule, and c squared is the mean square speed. In this topic, we have explored advanced mechanics including circular motion, simple harmonic motion, and gravitational fields. We have also studied thermal physics, including energy transfer, gases, and particle behavior. These ideas help explain many real-world systems, from satellites to engines. Thank you for watching.